Boom. Hello and welcome back to Trig Review Part 4. We are still continuing talking about the graphing of functions, so we will take a look at tangent and cotangent. We took care of the other 4. And then we'll move and talk about inverses later. So now the tangent graph is going to have y equals a tangent bx minus c plus d with the big change that the period now is pi over b. So the other 4 are 2 pi over b, and the tangent and cotangent are going to be pi over b. Now we have to learn the vanilla state first, right? The basic shape of tangent graph. We already seen that tangent is sine over cosine, and you can actually divide the points that you get and plot. But we can also just say what it is. So it's going to have vertical asymptotes at all places where cosine is equal to 0, because cosine is in denominator, right? And cosine is equal to 0 at pi over 2 and 3 pi over 2 and negative pi over 2. So it's going to have at all of these over 2, right? Pi over 2, 3 pi over 2, 5 pi over 2. Those are the locations for our vertical asymptotes. And the tangent is going to be like a cube, x cubed function, going to look like that. Going through this middle point, right, is going to be, the midpoint is going to be important point for us. And you see that the principal tangent period, because again you're going to have this going infinitely. These are terrible. You haven't seen those, all right? So the tangent will continue going forever, doing the same thing. I drew 2 periods right there. And the one that goes through 0, 0 is the principal one, the main one. And then I drew just 1 extra because I can. So there is not going to be a box with red lines. You are still going to have the green line because your midpoint is on the x-axis, and once the d kicks in, it's either going to go up or down for your midpoint. So if I draw, so let's immediately jump into an example. Let's say 2 tangent x minus 1. So amplitude A is 2, B is equal to 1, which means period is pi, and C is equal to 0, means you will go through 0, 0, and D is equal to negative 1, yes.
Wouldn't that top one be 4 pi over 2 instead of 3 pi over 2?
No, you go...
The dotted line?
Yeah, so negative 1/2, positive 1/2, positive 2/2, which is a pi, positive 3/2, positive 4/2, right? 1, 2, 3, 4, 5, 6, 7, 8. So you take a pi over 2 as a unit, and then you just have negative 1, 0, 1, 2, 3, 4 in front, placing these numbers in front. And then when you hit 2 pi times pi over 2, 2 times pi over 2, 2 and 2 cancels, you get a pi, right? And that's in mid. And also, the way I know is that the cosine graph, right, that's actually what I used, goes through pi over 2 and 3 pi over 2, because cosine goes through pi over 2 and 3 pi over 2. I know that's where my vertical asymptotes are, because cosine is in denominator, and that's where the cosine is 0, not allowed to have 0 in denominator, so that's where the vertical asymptotes are. All right, to draw this really vanilla problem for tangent, we are going to, again, no box in terms of red lines and stuff like that, but we are going to have these vertical asymptotes, which are left and right, and we are going to have the green line, which is the midline. So I'm going to draw the setup here. This is my x-axis, my y-axis, and immediately my green line is at -1. The problem has a c equals 0, which means no left or right shift. Maybe I should write that in blood over here just to make sure. So no left, right. So that means that your graph will go through the x equals 0, but on the green line. The period is pi, and as you can see over here, maybe I'm going to write this again, the blue, you have period divided by 2 on one side and period divided by 2 on the other side. Because the basic period of the tangent graph is pi, and you see the asymptotes at pi over 2 on either side. So pi over 2 on one side and pi over 2 on the other side, 2 halves give you a whole pi. So when we start messing with the period over here, right, when the period becomes 2 pi or pi over 3, whatever we come up with, you will go half of that period to the left and half of that period to the right to get your vertical asymptotes. So now in our problem, the period is pi, so we still have the asymptotes, which I'm going to use blue now because we don't have the box anymore, but we did use blue for left and right, so there we go. And again, those are at -pi over 2 and pi over 2 because half a period left, half a period right. Now, the only thing that it's not humanly possible to do very well is going to be amplitude. Remember how I talked about stretching functions, and I said that, you know, you really can't do great job on stretching functions like x squared or 2x squared or 3x squared. You just know it's kind of more squished and rises faster. And the same thing was for exponential and logarithmic functions. We kind of fudged that. So you can't do, you know, a stellar job at this. So you just put a standard tangent function through it, and whenever this curvature happens, right, like this big curvature here, you will put the amplitude there. Oh, come on. You will put the curvature there. So we don't actually pay attention almost at all to the amplitude of tangent and cotangent because, again, it is going to be a precise spot where it curves in precise amount and so on. So obviously calculus is going to address that much better in chapter 4. Right now you just wing it as long as you draw the cubic looking function through the determined midpoint, which is in this case clearly -1 over here because of your d. You guys are good to go. Let's shift tangent function. Let's shift tangent function. So y equals tangent, and also work with the period. So let's go with 1/2 x minus pi over 4 because we can. I'm not going to mess with d. That's easy, right? Go up or down for the green line. Who cares? So clearly I have a shift to the right, But as I said, if you have this, that shift is not this much. It's a different amount. You have to compute that amount. So the amount of the shift will be, well, first the period, oops, p, is pi over 1/2. So period is 2 pi now. Hey, nice. We have a good old period for sine and cosine. And we are going to find the midpoint, right? You don't have the start and end point now because you have asymptotes, but you do have a midpoint, the MP, right? And the MP is going to be 1/2 x minus pi over 4 equal to 0, which is going to be pi over 2, right? Is that pi over 2? Yeah. So move pi over 4 to the other side, and then times 2 each side to get rid of the half. So we have our midpoint at pi over 2, and we have our period at 2 pi. So we have everything. There is no d, so we are drawing everything on the x-axis, and we have to go to the left and to the right, so leave some space. We start by first placing the midpoint at pi over 2. And then you have to go pi to the right and pi to the left. So this, see, if this is pi over 2 from 0 to pi over 2, then twice that distance is a pi. So this distance is pi, and this distance is pi, to give me my period of 2 pi. And this is where we strike our vertical asymptotes through these points that midpoint plus minus half a period gave. So if you want the formula for asymptotes, I don't know if you like formulas. I generally avoid that stuff. So asymptotes are going to be at x equals middle point plus minus period divided by 2. So in our case, midpoint was pi over 2, and then you go plus pi minus pi because 2 pi divided by 2 is pi. So if you want the formula, there it is. I'm not too keen on those, but hey, some of you love it, so there you go. Guys, we are done. I have the midpoint and I have my asymptote guides. The function is not flipped, so I get to start in the lower left corner and just go through and curve up. That's the tangent. That's the tangent graph. We are going to label 3 pi over 2 and negative pi over 2. These asymptotes. Right, so meditate on this problem for another second, and we'll do another one and call it a day, huh? I mean, for the graphing, we still have other stuff to enjoy. You know where the door is if you don't want to, if you're already sick and bored and stuff.
What's the endpoint again?
There are no endpoints here. It's a midpoint MP. So there is a midpoint MP, which is calculated when you set the argument to 0, so that parenthesis. And from the midpoint, you will go half a period one way, half a period the other way to get your asymptotes. That's it. So tangent is actually much easier than sine and cosine graph. You have less steps, less things to worry about. We don't worry about amplitude, for instance, at all, because it's not humanly possible to do a great job on it. Next example would be y equals negative tangent of, let's go with 3x minus pi over 6 plus 1, just to make it as annoying as possible, and deal with this now. I will immediately start with the period calculation. So period is pi over 3. Great, right? And the midpoint calculation, because you need those. You have to start, everything has to start from the midpoint and the green line, right? You have to start there. So midpoint is 3x minus pi over 6 equal to 0. 3x is pi over 6. And x is equal to pi over 18 again. So I have x to be pi over 18. And the asymptotes, so VAs, vertical asymptotes, are going to be pi over 18 plus minus pi over 6, because pi over 3 divided by 2, that's like times a half, which is pi over 6. So this is p over 2, period divided by 2. If you do the common denominator here, times 3, so you have 4 pi over 18. And when you subtract, you have negative, so this is pi minus negative 2 pi over 18. Notice that I'm not going to reduce these fractions. I'm not going to reduce these guys because if I reduce these and I start counting here at 2 pi over 9 and pi over 9, which would work great for asymptotes, observe that for divisions, my midpoint will be at pi over 18, and I can't write that as over 9. You want all of the points on x-axis to be in the same denominator so that you can do proper divisions. So don't have pi over 2 mixed with pi over 4 and so on, because that introduces headache to draw stuff. Our green line is plus 1, so we'll leave just a tad more space on top. Set my green line through 1. And then midpoint is, I want to make sure, I think something disappeared, but looks good. So midpoint is at pi over 18. It really doesn't matter where you pick that pi over 18, so here it is. Pi over 18, but we know that the midpoint lives on the green line. And now I need 4 pi over 18, so that's 1, 2, 3, 4 pi over 18. And that is my right-hand vertical asymptote. And then I need negative 2 pi over 18, which is right here. And then that would be my other left vertical asymptote. I already have the midpoint. And then I should have done this earlier. You know, the word flip, because we need to flip, there is a negative sign. So instead of doing the cubic function from going from down up, you will go from up down. And we're done. I'll explain this problem from scratch, especially because it has this little bit esoteric numbers here, but it's okay. You can deal with that. So for the tangent graph, we start by figuring out the period, figuring out the middle point, and then we can start graphing. You will still do the D first. You already calculated your midpoint and your asymptotes, and you don't have to worry about A because it's not really user-friendly. Make yourself a note in whatever way that there is a flip, if there is one. Now, calculations. Midpoint is calculated when you set 3x minus pi over 6 to 0, and we get x is pi over 18. And then we are going to add and subtract half of the period, which is pi over 3 times half is pi over 6. We're going to add and subtract the period to the left and to the right to come up with locations for vertical asymptotes. Now, even though I can reduce these numbers, I am not going to do that so that I can have the same divisions. So if I call 1 squared pi over 18, that's just like calling it 1. It's 1 pi over 18, 2 pi over 18s, 3 pi over 18s, and then 4 pi over 18s, which is where the asymptote is. And it needs to be symmetric. I mean, you have 1, 2, 3 squares to the right, 1, 2, 3 squares to the left. Oh, you don't have square paper? Well, you can go right in the corner. When you go to the store, you have a $3 choice for the notebook with lines or $3 choice for the notebook with squares, and you make that choice. If you're taking math class or a physics class, I told you I come from a culture where you are kicked out, and 2 students will remain in this classroom if I had that pedagogy from where I come from. Like, oh, you have no square notebook, go outside and here's the ball to play. The rest of the life not in between. So yeah, there we go. And the flip, it goes right to this one. So again, you will graph the green line, that's the midline coming from the D part. I was at +1. And the only place where I lost points with this graph is that I did not label this point. So if you're interested in full credit, you have to label this point, otherwise don't worry about it. So I have to label that point if I want the full credit, which is pi over 18, 1. The rest is labeled. X and Y axes are labeled. All the asymptotes are labeled. And everything is great. The cotangent is just going to look different, and it has one major change. For 5 functions, you will be setting the start point or the midpoint equal to 0. Cotangent is the only one where you set it equal to pi over 2. And the reason for that is, where's my glue that I used before? If I draw a basic tangent graph over here on the board, here's the basic tangent graph with its asymptotes. And now here's the cotangent graph, again, vanilla, basic, looks this way. Observe, start point starts at 0. Start point starts at x equals 0. This way, the start point for the sine, which is equivalent this side, again starts at 0. Start point, again, starts at 0. Midpoint is at 0. Do you see that all of them start at 0, all 5? Now look at the cotangent, pi over 2. So these 5 guys over here, these 5 guys over here will all have parenthesis equal to 0, which is bx minus c. This is the only one, bx minus c equals pi over 2. So that's, I mean, you're in school to learn stuff, so yeah, learn it, right? So the rest is the same as tangent. So let's do a cotangent graph. We'll work on some, let's put some spice into it. Cotangent of what should we put? Cotangent of 1/2 x minus 2 pi over 3, just to make it annoying, and leave the d out, who cares. Alright, there we go. Alright, so it's gonna be 2 pi over 3 over there, is gonna be very interesting, but such is life. So immediately, you know, I start with figuring out period, which is pi over b, which is pi over 1/2, which is 2 pi in this case. That means for asymptotes, pi on each side. Pi to the left, pi to the right. I forgot to write the midpoint. So whatever the midpoint is, you go pi to the left and pi to the right, because 2 pi is the full period. So that's where the asymptotes are. Midpoint calculation, well, that's the new part. 1/2 x minus 2 pi over 3 is equal to pi over 2. And I'm just going to put the red flag right there. Is the blood dripping down? There we go. So you know it's a problem. So the only one where you set the parenthesis equal to something is not 0, pi over 2. 1/2. First, what I'm going to do to solve these problems that have these multiple fractions and everything, the fastest way is to multiply through with a common denominator and kill all the fractions in one shot. You learn that in elementary algebra and hopefully persists with you. So yeah, I can move 2 pi over 3 and then go the common denominator and then, you know. But I can also multiply everywhere by 6. Entire formula times 6 to kill fractions. So now my problem is when I do the 6, I get 3x minus 4 pi, right? Because 6 and 3 cancel, so times 2 equals to 3 pi. And now 3x is equal to 7 pi when I move 4 pi to the other side. And finally, x is 7 pi over 3. Whew. That's your midpoint. Disgusting. That's okay. So midpoint, which is this point here, right? The midpoint is at 7 pi over 3. Plus minus pi for asymptotes. So 7 pi over 3 plus minus pi for asymptotes. All right. So plus pi, that will be 10 pi over 3 for the one on the right. And then minus pi is 3 pi over 3, right? Because, no, 4 pi over 3. I lied. Because 7 minus 3, right, when you do the common denominator. So I have the asymptotes now. Everything is in thirds, as you can see. And I'm going a lot to the right. So I'm going to leave all of the space to the right. I'm going to hang around the x-axis because there's no d part to go up and down. So leave the same amount of space on top and the bottom. And everything is in thirds. We are talking about these values. So I need 10 tick marks because the largest numerator is 10. And then we're going to call each tick mark pi over 3. And you will have 10 pi's over 3 on a pile. So just count. 1, 2, 3, 4, 5, 6, 7 is the mid. 8, 9, 10 is the asymptote. So we have the asymptote at 10. And then asymptote at 4. 1, 2, 3, 4. And then you can check if the amount of tick marks on both sides of MP is the same. I have 1, 2, 3 squares, 1, 2, 3 squares. We are perfect. We are going through this point, which is 7 pi over 3. Is it flipped? No. So we just draw the standard cotangent graph which is backwards of a tangent, and you walk away. No green line because there was no D. Clearly it's shifted because we do have C, and the period is not pi because we had B different than 1. I hope you find this very structured. Well, it's overwhelming because you just tuned in, but I hope you find this very structured, and if you guys practice this, the graphing will go really easy. So that's it for graphing. We spent good 2 hours on covering all 6 of these guys. Well, hour and 2 hours on covering graphing in detail. I will remind you that in the calculus you do not have graphing calculator for exams. You can use your graphing calculator in the homework and stuff, but you will be cheating yourself because you will not be acquiring knowledge and speed to survive exams. So the everlasting complaint, oh, but all my labs are 100 and the homework is 100, but I can't do tests. Of course you can't do tests if you are relying on a calculator which you don't have. Graphs are a very big deal in calculus. A lot of trends need to be picked up off of the graphs, and you can't sketch these guys quick enough in calculus. You take 30 minutes to, work this one graph. You're not gonna have time for the calculus part of the question if you spend 30 minutes doing the pre-calculus prerequisite thing that needs to go this way. So practice these basic skills. And again, what I said, the calculus questions for graphing will be, let's say, tangent squared of x minus 2, or tangent of ln x, or e to the sine x. So some crazy stuff like that with the function composition. But then we have more powerful tools. Right now you only have arithmetic tools, which is, plus minus a number to shift it left, right, up, down, or times a number to swoosh it or stretch it. So those are all arithmetic changes that you can apply to the graph, and that's what we study in PreCalc in 1.6 applied to all functions ever. In calculus, you get function composition going on. In chapter 4, you learn the first, second derivative tests, concavity, and critical points, inflection points, and a lot of cool stuff that will help you with these more complex graphs. So that's the end of the part on graphing. The last part for today to discuss is the part on inverse trig functions. And again, Monday is off, no class. There is a class on Tuesday, there is a class on Wednesday, and then you will take your placement test either on Thursday, Friday, or Saturday. Please call and check the hours. The main entrance is closed. You can't get in the school through the main entrance. You have to use the small, tiny entrance next to the theater to go to the testing center and take the placement. The price of the placement is $10. It's already included in the price, so it will be free. Make sure you bring your ID with the current face configuration, and they will allow you to take the placement test. You can place back into PreCalc 1, PreCalc 2, or Calc 1, depending on how well you test on the exam. And do I have anything else? And go, if you haven't taken yesterday the packet to practice, to see what the problems look like and so on, make sure after the class today you go and pick up that packet so you can work it out. I will answer any questions you have from that packet on either Tuesday or Wednesday during class, or briefly afterwards. It's fine if you have something that you don't think is public. And the test contains all of the courses: pre-algebra computation, algebra 1, algebra 2, elementary and intermediate questions like polynomials and graphing and all that kind of stuff, linear lines, slopes, and then PreCalc 1, including exponential, trig, and then PreCalc 2 with trig and so on. Yes?
The test is also online. So if you go to the Rare Valley website, you go to the testing center,
Uh-huh.
it gives you all the active placer links to even practice tests online as well.
Perfect. Are those the same? Did anyone?
It's the active placer. We should be. I mean, I didn't think.
No, I mean if the paper is the same, because there might be additional, like different kind of practice, which means that just have bigger base if you pick up the paper, and then you have the online as well. So maybe extra problems are included. So yeah, go to the testing center website. When you are on that website, also check the times, right? And if they close at 4 or 4:30, don't come in 30 minutes prior to close time, because that's when they leave. So they will cut you off in 30 minutes, and then you're back in algebra. Show up at least 2 hours prior to closing time. The best thing is obviously right when they open. Your brain is the freshest at the earlier it is. Now you might want to argue differently, but you're not going to win the argument. So don't. Inverses, and then lunch. Inverse trig. Great. I always start talking about inverse trig by going back to 1.8, because this is 1.8, just applied to trig. And in 1.8, we learned two concepts related to the inverse. One concept is that the inverse swaps domain and range, which means you swap x and a y. And the other thing that we talked about is that the input and output are switched, which means that if you compute that f of x is equal to y, right, this way, then the inverse of y will give you back your x. So it's like the undo kind of situation. Now that applied to your trig in the lamest possible terms means sine of the angle is equal to a number, and then inverse sine of the number will give you back the angle. So that is the biggest thing to realize, and I will box this. This is not mathematically correct and perfect notation, but this is the essence of what's happening here. So to give immediately example of this, sine of pi over 3 is equal to 1/2. Inverse sine of 1/2 is going to give you pi over 3 radians angle as a result. So it's literally undo. You will use the same chart of values that I drew the other day, which you should be able to construct in about 20 seconds by now, because you practiced and you care. So if I ask you what is the inverse tangent of 1, you will immediately say, oh, it's pi over 4 or 45 degrees. Because you look at the same chart that we had before. So we are not learning new values. We're just going to redefine things to fit the inverse. So inverse tangent of 1 is going to be pi over 4, right? Calculating inverses is very important, because on Tuesday we are going to switch our trig functions and graphs towards trigonometric identities and then trigonometric equations. Trigonometric equations are very important, just like exponential and log equations, because in calculus you have to solve a lot of trig equations and you have to compute a lot of trig functions. So it's very important for you to know how to deal with those. So tangent inverse of 1 is pi over 4. You can try to figure out what is the secant inverse of 2. Right? Secant inverse of 2. Well, what should we do in this case? Well, instead of doing secant inverse of 2, you will take a look at the cosine inverse. You get this stuff. What? No. Half, because they give you the same value, and because you know that the secant is 1 over cosine, And cosine 1/2 will give you √3/2. Therefore, cosine of 1/2 is pi over, that's what I meant, pi over 3. Wow. So secant inverse of 2 is pi over 3. There we go, much better. Wow. So these are different examples. All right. And then again, different example. I'm just gonna separate all the examples. So cosine of pi over 3 is 1/2. Therefore, the inverse cosine of 1/2 is pi over 3. And then, because secant is 1 over cosine, so what used to be opposite hypotenuse over adjacent now is adjacent over hypotenuse. So the 2 switches into 1/2. The main issue is the issue with restricted domains and the problems that the inverse is actually not a function for all 6 trigonometric functions, and we have to fix that. We have to use inverse trig functions a lot in calculus, especially inverse sine and inverse tangent. They show up a lot. The graph of inverse tangent pops in frequently in Calc 1 and Calc 2, and then differential equations. So we primarily focus on sine and inverse tangent, and we particularly focus on the inverse tangent graph. There is a big deal in calculus with inverse tangent and somewhat inverse sine, and then the differential equations introduce inverse secant as well on some level. So to start off the issue and understand the issue, we go with the vanilla sine x graph, which when we graph on its infinite wave like this, clearly fails horizontal line test. So that means that as you draw your inverse sine graph, it's not a function, because it is going to do this wavy behavior along y-axis, which fails the vertical line test miserably. So actually, out of the box, inverse trig is not a function. So we have to fix that. We have to fix that because we have to use inverse trig in calculus, and calculus applies strictly to functions, which is the reason why you do function analysis of functions in pre-calculus courses. The way to fix this, and we did this with the x squared graph, was to cut out the domain in such a way that whatever is left passes horizontal line test, therefore would pass the vertical line test on the inverse side, and the inverse will be a function and therefore usable in calculus. So what I'm going to do now to fix this, fix the issue, I am going to restrict the domain of sine to negative pi over 2 to pi over 2. So now new and improved sine x graph, all chopped up, is going to go like this. So this is our new and improved graph. Because, why is it improved? Because, yes, we threw a lot of stuff out. But you still have enough to see it's a sine graph. And you also pass horizontal line test, which means now you have inverse function. And if you have inverse function, you can do stuff in calculus. Calculus applies to functions. Derivative of a function, integral of the function, limit of a function. Right, so it's very important to have functions. Now you can quickly draw the pick up the points, x, y points, and you know that for inverse you just need to swap x and a y. So we have a negative pi over 2 with a negative 1. We have 0 with 0, and pi over 2 with 1. So now if I want to construct, and this is now red, ugh. Does anyone have the Apple product you don't need? I want to break something. Now, is this going to be the crash train, or is it just going to be an isolated incident? We didn't have any crashes yesterday, so I guess it's due to happen today. All right, let's go. Sine inverse of x. So for sine inverse of x, I'm going to pick the points, but I'm going to swap them. So I have negative 1, 0, 1, negative pi over 2, 0, pi over 2. And the graph, 0, 0, negative. So now we have another crash. Good. Ah. Maybe I should go back to my Windows 8.1 and Surface 3 so I don't have this. It didn't crash once on the Surface 3. Surface 4 plus Windows 10 crashes every day. X-axis now. I did this thing wrong. I forgot where I stopped. So when you swap, this is negative 1, 0, 1. Negative pi over 2, 0, pi over 2. So here we have negative 1 and 1 on x-axis now, and pi over 2 and negative pi over 2 on y-axis. So I have these points, and there we go. And that would be the graph for inverse sine. Now, can we shift this one left, right, up, down? Sure, it's a function. All I need to do is to go x minus 3 or everything plus 2 or negative in front. I can do any of that stuff to apply 1.6 and move this anywhere I want. The next order of business, just don't crash, all right, is the inverse cosine, sorry, of x. Again, I have to cut the cosine graph. Now, the cosine graph is going to be cut differently. Each one gets cut differently on a domain because of the each graph is its own shape. So you see that the sine graph was cut from negative pi over 2 to pi over 2. Cosine can be cut from 0 to pi. So y equal cosine x 0 to pi cut, which gives us this squiggle. That's it. So now what is the graph for cosine inverse? Graph for inverse cosine. So what are the points here? X and a y. The first point we have is 0, 1. The second point we have is pi over 2 and 0. And the last point we have is pi and negative 1. So now you will take the same points and you will apply those points here. So, great, I don't have space. So pi over 2 and pi, -1 and 1 on x-axis. So we start with the 1, 0, 1, 0, and then this one, and then this one, and then we fit the cosine sideways through these points. And there it is, inverse cosine. Shift up, shift left, whatever, you can add number to x, you can add the subtract number from the whole thing, you can reflect it on axes, you do whatever you have to with 1.6, but as long as you learn the basic graph and the way to quickly get, you just don't want to memorize everything in PreCalc 2. There's so much. So you try to kind of cut corners as much as you can. And the last graph that we really need to discuss is a tangent graph. We don't actually worry about other graphs too much, but the tangent one is, you know, really the one that you will need later. We start again with considering the vanilla state over here with the cubic looking one. And then we realize that if we are to draw the inverse and draw the first tangent, then there will be another one on top, there will be another one on the bottom. And clearly that would not be a function if you stack infinitely many inverse tangent graphs on top of each other. So again, we have to settle for one of these graphs. What happened now? So we do the principal graph over here, and the principal graph is this one. So we are on a domain -pi/2 to +pi/2, right, domain, which means that for our inverse, those two domains will be our x and a y asymptotes now, and the tangent graph, inverse tangent graph, will go sideways through these. It's a terrible looking inverse tangent graph, so let me... it's better. And that's inverse tangent. So that's our inverse tangent graph, and that takes care of this issue. The very last thing, and I know, I think, Olga, you mentioned it with a negative sign in front of B. Mm-hmm. So one thing that we did not discuss, and that goes across all of this inverse included, is what happens if you have negative B. And that goes back, we don't consider that much, because that goes back to a concept of even and odd functions, which makes sense to define now. So even and odd trig functions, if you go back to your chapter 1, which is where most of the function knowledge database is, you find that odd functions are defined as f of negative x is the same as minus f of x, and even functions are defined as f of negative x just gives you back original f of x. So now, if we make the category over here for even functions and odd functions. So here's the odd part, and here's the even pile. In the odd, you have your sine x, you have your tangent x, you have your cosecant x, and you have your cotangent x. And in the even part, all you have is cosine x and secant x. So this is the way they split on even and odd functions. So now, as you can see, it really, negative b doesn't do much other than annoy probably left and right shift, but other than that. So if you start with y equal sine of negative 2x like this, by the property of the odd function, that minus will jump in front and become a minus sine of 2x. So technically the flip becomes also the vertical flip for the whole thing. If you have the same thing for cosine of 2x, by the property of even, you just delete it. It's just like it's not there. So you actually see that you never work with negative b. Your period can never be a negative number because period is the distance between 2 points. You will never call the distance to your house negative 10 miles, right? So it's always, when you're home, RVCC is say 10 miles away. When you come to RVCC, your house is again 10 miles away. It's never negative 10. Distances are always positive, and a period is a distance, right, in space. So the b will never return a negative value, and because b is never negative, right, we can take the even and odd. Now just go ahead and apply the same thing for secant and tangent and all of these guys according to where they belong in the list. And now their inverses fit in the same category, so you have 4 odd inverse and 2 even inverse trig functions. The only only time where this is important is when you have the c. Then it actually messes things a little bit up, but not big. And this goes back to that problem where I had, remember, we factor minus when it had the e exponent and we had the evil one. So that would be the equivalent evil one for trig. So here, evil one, you have y equals, let's say, I don't want to go secant because secant, let's go with a cosecant of negative 2x plus pi over 4, right, as a function. So now I'll write in red factor. So when you factor that one, you will get cosecant of negative 2x, and here is the great killer. The plus pi over 4 switches to negative pi over 4. So what used to be shift to the left is actually shift to the right because we factor the minus. And now this minus sign jumps in front because cosecant is odd. And you have 2x minus pi over 4. You will graph sine. You will flip the sign because of the minus. Then you will cut down the green line and invert the cups to get the cosecant graph. So this is the evil case when you have a negative b and c, and then the sign of the c changes. So what looked like is a shift left is actually shift to the right. We've seen these problems earlier, PreCalc 1 review. We did that e to the 2 minus x or whatever we did. So that's the same deal here. Again, it comes from 1.6. 1.6 applies to all functions in the galaxy. It doesn't matter when you learn those functions. So all of these shifts, all of these inverses, all of the function compositions, everything you learn, domain, range, x, y intercepts, the entire chapter 1, the most important chapter of PreCalc book, is applied to all functions, which are polynomials, exponential, logarithmic, trigonometric, in Calc 2, hyperbolic functions, all of those, and then thousands of others that we don't learn in elementary math courses. All of those obey 1.6, 1.7, 1.8, and so on. So all we did today, 1, 6, and 1/8 applied to trig. 2.5 hours of doing chapter 1 again, right? And then domain, and then the range, right? And inverse, so on. So that's it for today. I will see you all on Tuesday. Back for more. Bye.